The lab is dark except for the dim glow of a display screen. A woman in thick glasses watches as single green points of light appear, one by one. Each is an electron fired through two narrow slits. With no detector watching, the dots arrange themselves into alternating bands, a wave pattern, but she needs to know which slit each electron passes through. She sets up a measurement at the opening. The moment the detector activates, the pattern collapses. The dots scatter randomly. No force touched the electron. Nothing pushed it. She leans back. The question presses in silence. What exactly changed when we looked? Not the electron, not the equipment. Something else is happening here, something we cannot see. What really is a measurement? To answer that question, we travel back 2 centuries before that dark lab. In 1801, a man named Thomas Young sat in a room with a candle, a thin card, and a screen. He cut 2 slits in the card and let light pass through. On the screen, he expected 2 bright strips. Instead, he saw bands of light and dark, evenly spaced. He had drawn a picture of a wave spreading through gaps, crests and troughs, adding and cancelling. It was the first mathematical proof that light was a wave. 160 years later, a physicist named Klaus Janssen tried the same experiment with electrons. He fired them one by one at 2 slits. They struck the screen as individual points, but slowly, those points arranged themselves into the same alternating bands. The electrons were behaving like waves. Here is where the puzzle sharpens. Janssen placed a detector at one slit to sense which path the electron took. The moment that detector was active, the bands vanished. The electrons collected in 2 simple piles, like bullets from a gun. But the critical detail is this. The detector did not need to be watched. It did not need to be connected to a screen or a human mind. It could simply be a device that recorded its measurement to a hard drive that no one ever checked. Even then, the pattern was destroyed. The presence of the measurement alone was enough. So the mystery is not about consciousness. It is not about a person looking. It is about the physical act of measurement itself. But if a mind does not cause the collapse, what does? What is the observer? Not you, not your eyes, not your brain. Then what? But that answer, that a mechanical detector alone collapses the wave function, did not sit well with everyone. One man in particular refused to accept that the puzzle was solved so simply. Eugene Wigner, a Nobel laureate in physics, spent sleepless nights obsessing over the boundary between mind and matter. He was born in Budapest in 1902, a quiet man with thick glasses who helped design the first nuclear reactor. Yet what haunted him was not nuclear fission. It was the measurement problem. He imagined a friend. The friend sits in a sealed lab, measuring the spin of a particle. To anyone outside, the friend should be in a superposition of seeing both outcomes. But that is absurd, Wigner argued. The friend experiences a definite result. Consciousness, he said, cannot be split. Therefore, the collapse of the wave function must occur when a conscious mind becomes aware. This shifted the entire question. If Wigner was right, then consciousness is not a side effect of brain activity. It is fundamental, built into the structure of reality. The universe exists, he wrote, only as a correlation between conscious observations. No one knows if Wigner was correct. Some call his view deeply insightful, a recognition that mind and cosmos are woven together. Others call it desperate anthropocentrism, placing humanity back at the center of a universe that dethroned us long ago. The experiment that seemed to rule out consciousness did not, in fact, settle the debate. Wigner's midnight question still lingers. What is the observer? Wigner's question assumed the observer exists in the present, deciding the outcome at the moment of measurement. But what if the observer can make their decision after the particle has already finished its journey? That is the question John Wheeler took up in the 1970s. Wheeler was a student of Bohr, a wiry man with a wild shock of white hair who thought in cosmic scales. He imagined a photon from a distant quasar, traveling for 10 billion years toward Earth. Along its path, a galaxy's gravity bends the light like a lens, splitting it into 2 possible routes. By the time the photon nears our detectors, Wheeler asked, has it already chosen one path? He proposed a delayed choice experiment. After the photon has entered our telescope, we suddenly decide whether to measure which path it took or to let the paths recombine. If we choose to measure which path, it acts like a particle. If we choose to let them combine, it acts like a wave. But the photon passed that galaxy 10 billion years ago. Our choice now seems to retroactively decide what it did then. This was a thought experiment for decades, until 1999, when a team at the University of Maryland made it real. They used entangled photons, pairs created together, linked so that measuring one instantly reveals information about the other. One photon went straight to a detector, the other traveled through a system that encoded which path information. After the first photon was already detected and its position recorded, the team made a choice. They either kept the which path information or erased it. When they erased the information, the interference pattern reappeared in the results of the first photon. The first photon had already hit its screen. The choice to erase happened later, yet the pattern changed retroactively. Here is the careful part. The erasure only affects the pattern when you later compare the two photons' data. You cannot send a message backwards in time because the results are random until someone correlates them. But the correlation itself shows that the decision to erase seems to reach back and alter what the first photon did. The photon does not know if you will check its past. It behaves accordingly when you compare notes. This forces a deeper question. Is the universe keeping a record? Does the cosmos care whether we know the path it took? The past, Wheeler suggested, is not a fixed set of events. It is a collection of possibilities that only become definite when a measurement is made. And that measurement does not have to happen before the event. It can happen after. Wheeler's delayed choice experiment showed that the decision to erase information can retroactively affect a particle's behavior. But that only works because the which path information is stored in an entangled partner. The deeper puzzle remains. In everyday reality, what forces a quantum system to settle into a single outcome? The answer most physicists now offer is decoherence. Imagine an electron balanced between two possible paths. In perfect isolation, it remains a wave of possibilities. But isolation is a fiction. The electron constantly jostles against stray particles, passing photons, the vibrating atoms of its surroundings. Each collision entangles the electron's state with that particle. The two potential paths now leave faint copies, footprints, in the environment. Once the environment has recorded which path the electron took, the delicate interference between the two possibilities vanishes. The superposition has not collapsed. It has leaked out into the environment, spreading across countless particles until it becomes impossible to reverse. The electron now behaves as if it chose one path, not because anyone looked, but because the universe itself looked. This process, decoherence, happens everywhere always. It is why a baseball never exists in two places at once. The baseball interacts with air, light, the ground, entangling its position with trillions of particles. These interactions effectively measure its location, erasing quantum strangeness and producing the classical world we inhabit. No conscious observer required. Decoherence seems to solve the problem, but it introduces a new one. Decoherence explains why the alternatives become invisible, why interference disappears. It does not explain why we experience only one outcome. The wave function still contains both possibilities, they just no longer interact. Why does the baseball land in the glove and not the outfield? In theory, both happen in different branches. Decoherence alone cannot pick one. It only describes how the branches separate. This is the decoherence divide. We have pushed the mystery one step back. The question is no longer what causes collapse, but why there appears to be a single definite reality at all. The universe may be observing itself every moment, but it has not yet told us why it chooses one story over another. Decoherence pushes the mystery back, but it does not solve it. It shows us how the universe splits into branches that can no longer talk to each other. It just refuses to say which branch we are on. In the late 1950s, a young physicist named Hugh Everett sat down and looked at this problem, and decided to accept the branches as equally real. Everett proposed that the wave function never collapses. Not because of measurement, not because of consciousness, not ever. When a quantum system interacts with a particle, both evolve together, becoming entangled. The system and the particle split into multiple branches, each containing a different outcome. But the wave function as a whole continues to evolve smoothly, containing all possibilities. There is no special moment where one possibility wins. There is only branching. In this framework, observation does not mean collapse. It means entanglement. When you measure an electron's spin, your own atoms become correlated with the electron's state. You split into multiple copies, one for each outcome. Each copy believes they observed a definite result. But the original you never collapsed into one. You simply branched. The feeling of a single outcome is an illusion created by the fact that the copies no longer interact. This idea comes with an immense emotional weight. Every quantum event, every random decay, every photon that could go either way, every choice you think you make, produces a new branch. There are unfathomably many versions of you, each convinced they are the one real version. Some of those copies are reading this sentence right now, in worlds almost identical to this one. Others are living lives that diverged from yours long ago. Your identity is not unique. It is one leaf on an infinite tree. And this raises the final question. If every possible outcome happens somewhere, what does observation even mean? The observer no longer plays a special role. They do not create reality. They just follow a path, blind to all the others. The act of looking no longer collapses anything. It just adds another layer of branching. Observation becomes a word we use to describe the experience of being on one branch, unaware of the infinite copies we left behind. But if everything happens, does any single observation matter? Everett's branching universe leaves us on an infinite tree, surrounded by copies of ourselves. But here is where the abstract meets the concrete. The same process that creates those countless worlds, decoherence, is the central enemy of a technology that could reshape our future. Quantum computers work by exploiting superposition, the ability of a particle to be in multiple states at once. A quantum computer with enough qubits could, in theory, explore many solutions simultaneously, cracking problems classical machines never could. But there is a catch. Every interaction with the environment, every stray photon, every vibration, acts as an observation. It entangles the qubit with the outside world. The superposition leaks out. The computation collapses. For decades, decoherence was the problem engineers fought. They built ever more isolated systems, cooling them near absolute zero, shielding them from every possible disturbance. But noise always remains. Then 2024 arrived. In two separate experiments, teams at Harvard and MIT and at Google demonstrated a new kind of quantum error correction. They built logical qubits, groups of physical qubits storing information redundantly. When one qubit loses its quantum state, the others detect the error and correct it without ever measuring the qubit directly. By encoding information across multiple entangled particles, they can spot when decoherence has happened and reverse it, keeping the superposition alive. Think about the irony. The very process that splits worlds is being tamed. We are learning to manipulate the boundary between quantum and classical to allow superposition to survive just long enough to perform a calculation. We are building machines that exploit the very mystery we cannot explain. What does an observation mean? We still do not know, but we are already using it. So the physicist returns to the screen. A particle arrives, a flash. After a century, we still cannot agree on what that observation means. We have built machines that rely on superposition, corrected errors we barely understand. But the act of measurement itself remains a mystery. You are watching this. You are an observer. What does that make you? A participant in reality? The question is yours now. Thank you for watching. Share your perspective in the comments.